Our first set of examples here are going to deal with significant digits, and then precision and accuracy, types of error, and finally scientific notation. Okay, so we need to determine the number of significant digits, and I had some examples here that disappeared. I don't know where they went. Oh no, I just have an extra slide. So we want to determine the number of significant digits. Well, my first example here has 1, 2, 3, 4, 5, because every non-zero digit is significant. My second example, none of these zeros are significant at all. So this one actually only has one significant digit. This example has 6. A zero that's in between two non-zero digits is significant. So 1, 2, 3, 4, 5, and then the last 0 is actually also significant. A 0 to the right of the decimal and simultaneously at the end of the number is considered to be significant. So then the same thing would be true here. 1, 2, 3, 4, 5. And then there's no decimal at the end of this number, but there is this bar above the 0, so I know that that is going to be my last significant digit. 1, 2, 3, 4, 5, 6. And then similar here with the little squiggly above that 0, I know that's going to be my last significant digit, so 1, 2, 3, 4, 5, 6, 7. So let's talk about error now. Jane measured a picture that was supposed to be 8 by 10. However, her measurements were 7.98 and 10.24. So we want to figure out her error. So we want to start with her absolute error, and that is the approximate value, or what she measures, minus her true value. So 7.98 minus 8 and 10.24 minus 10. So this is negative 0.02. And this is 0.24. And then we also want her relative error. Well, her relative error is the absolute error divided by the true value. So her absolute error, negative 0.02, divided by the true value, which is 8. And 0.24 divided by the true value, which is 10. So negative 0.02 divided by 8 is negative 0.0025, and 0.24 divided by 10 is 0.024. And then finally, the percent error is just the relative error times 100. And so for our first dimension here, our percent error is negative 0.25%. And for our second dimension is 2.4%. All right, So now we're going to perform some calculations. What we need to remember is that when you add or subtract numbers, the result is only as precise as the least precise number. And so this is our least precise number. The more precise, the more digits after the decimal you have. So since this has the fewest digits behind the decimal, it is the least precise. So then let's add these together. 3.567 plus 5.2 plus 6.78 is 15.547. But we want it rounded to the correct number of significant digits, which means I should only have one place after the decimal. So if I look back at the number after the 5, we end up with just 15.5. And then we want to multiply 4.503 times 8.02 times 2.7912. And when we are multiplying, our answer can only be as accurate as the least accurate number. And the least accurate number will have the fewest number of significant digits. So this one has 4, this one has 3, and this one has 5. So this is our least accurate number. I need to have 3 significant digits in my answer. So when I multiply, I get 100.8016. I need 3 significant digits, so 101. All right, so scientific notation, we want to write our number as the product of the significant digits written with exactly one non-zero digit to the left. So 3.45 would be the significant digits, and a power of 10 times 10 to the, well, if my understood decimal is right here, 1, 2, 3, 4, 5, 6, times 10 to the 6th power. When we have a really big number that we're writing in scientific notation, our exponent is positive. So the second one, 4.567, and times 10 to the, we're going to move this 1, 2, 3, 4 places. And because it's a small number, it's to the -4th. So now I want to expand. So 4.9205 times 10 to the 3rd means I'm going to take this decimal and I'll make this number bigger. 1, 2, 3. I move it 3 places to the right. And then here, 7.08 times 10 to the -7th. I'm going to take this decimal, move it 7 places to the left. And I was able to rewrite and expand that number.